Hello everyone, and welcome back. Today we're going to continue our exploration of single variable calculus and focus on a very important tool known as the derivative of a function or a relation. Let's quickly go over just a couple of the basics that we need in order to derive the motivation and purpose of what a derivative actually is. Recall that the average rate of change of a function f on an interval a, b is defined to be equal to the ratio f of b minus f of a over b minus a, which tells you on average whether the function is increasing or decreasing over the course of some interval that has a length bigger than 0. So if we look at a picture here, so let's assume that this is an arbitrary function. Let's call it f. Let's assume that this is the x-axis and this the y-axis. Obviously, if we choose this interval a, b, obviously there's an interval for which this curve is decreasing, which is going to be, for example, on the interval a to c. And the function is obviously increasing on the interval of, say, c to b. But if we were to connect these points a and b with a line, or a f of a and b f of b with a line, then the slope of that line we see obviously is positive. So we say that on average the function is increasing on the interval a, b, and the slope of that line can be generated from this average rate of change formula here. But what we want to do is not to get the average rate of change over the course of the interval, but rather the exact change at a particular point. So for example, if we take or find the slope of the curve at this point exactly at A, notice that that tangent line is going to be decreasing. Notice that at that point, B f of B, the slope is going to be increasing. For example, you could also choose another point over here. For example, we could choose this point and find the tangent line, and that slope will be increasing, but not as increasing as, say, B f of B, right, the point on the right. So at every single point on this particular relation, we should be able to find the slope of the associated tangent line, and derivatives are going to allow us to find that. So how are we going to build that particular relation? So what I'm going to do is I'm going to draw practically the same exact picture. Let's assume that this is the curve for which we want to find the derivative of, is what we're going to say at a particular point. So let's consider, for example, this point x, and let's assume that we have a point in the future of x whose distance is epsilon away from it. So if that is epsilon, that means this point is going to be x plus epsilon, and epsilon is going to be a small but positive number. So if we look at the functional values here, this value would be obviously f of x. This value here, associated to x plus epsilon, would obviously be f of x plus epsilon. And let's assume that we want to find the slope of the line that passes through these points, i.e. The average rate of change. So what we want is to find the slope of the line at exactly x. So what we can do is we can make this distance really close to 0, and that's going to give us a better approximation to it. So how can we make things arbitrarily close to a number? Well, we actually already know how to do that. That would just be via limits. So obviously the slope of this line at the point x, which I guess we could write also as f of x, yeah, we can write it like that. So this is going to be equal to the limit as epsilon approaches 0 of the average rate of change relation. So f of x plus epsilon minus f of x divided by x plus epsilon minus x. Right? So what we're going to do is we're going to make this distance really close to 0, and these slopes are going to hopefully get closer to the slope of the curve that we are aiming for. But notice that there is some algebraic simplification in this formula here. Notice that there's an x and there's a minus x there, and therefore we see that the slope of the function f at the point x is going to be equal to the limit as epsilon goes to 0 of f of x plus epsilon minus f of x, all divided by epsilon. And some people will use the letter h to represent epsilon, the number that gets arbitrarily small, but it doesn't really matter as long as you stay consistent with your notation. So what is this? Well, this is the slope of the curve f at a point x f of x. All right. So this is the slope of f at x f of x, which obviously is a point belonging to the relation f, right? So The slope of course, depends on the direction, but typically we refer to the slope of a function at a particular point as synonymously as the derivative of f at x f of x. So slope of a curve at a point is synonymous to the derivative of a curve at a point, typically said. So we can write this instead as dx of f is going to be equal to the limit as epsilon goes to 0 of f of x plus epsilon minus f of x all divided by epsilon. And this is, again, what we refer to as the derivative of f, and some people will say at the point x, f of x. Right? So that's the definition of the derivative. So let's actually work through a computational example to find the derivative of a particular curve at a particular point. So let's assume we're interested in finding the derivative of f at a particular point x if the function f of x is equal to x squared. And let's assume that we're actually going to be interested in evaluating this derivative at x is equal to 3. So what is the slope of the curve, x squared, when x is equal to 3 is the question that we're trying to answer. So if we use the definition for which we have derived from the average rate of change, what would the arbitrary derivative of the function f at any point x be equal to? So the derivative of f at any point x is going to be the limit as epsilon goes to 0 of f of x plus epsilon minus f of x all divided by epsilon. So what we're going to do is we're just going to replace x with x plus epsilon, because if f of x is equal to x squared, then f of x plus epsilon is the same as x plus epsilon squared. So this becomes the limit as epsilon goes to 0 of x plus epsilon, the quantity squared, minus x squared all divided by epsilon. So now what I want to do is expand this quadratic term out, so it's going to be equal to the limit as epsilon goes to 0, and once you expand it, you're going to get x squared plus 2x epsilon plus epsilon squared minus x squared all divided by epsilon. And if you notice here, notice that we have an x squared there, a negative x squared term there, so they cancel. And what are we going to be left with there? So we're going to be left with the limit as epsilon goes to 0 of 2x epsilon plus epsilon squared all over epsilon. Obviously, this epsilon needs to cancel for us to evaluate this limit in an algebraic fashion. So obviously we have an epsilon on the top because we have the limit as epsilon goes to 0. If we factor out an epsilon, we're going to have epsilon times 2x plus epsilon and epsilon on the bottom. And we see that these epsilons will cancel. And we're just going to be left with the limit as epsilon goes to 0 of 2x plus epsilon, which is just a linear function that's shifted up or down by a factor of epsilon. And epsilon is typically assumed to be a positive number, so that's just a line that's shifted up. So obviously this function is continuous, so we can just plug in the epsilon value for 0, m, and we're just going to be left with 2x plus 0, which is equal to 2x. So that's the derivative of f at any point x. So that means the derivative of f at the point x is equal to 3 is going to be equal to 2 times 3, which is equal to 6. So if we look at our curve x squared, which we know is going to be equal to this, then what we're asking is, okay, if we look at the point 3 comma 9, which is that point there, what is the slope of the line tangent to the curve at that point? And according to the derivative, the slope is equal to 6, and that's what the derivative, at least in this context, will tell you. Let's work through another example on how to find the derivative of a function via the limit definition. So let's assume that we're interested in finding the derivative of the function g at the point when x is equal to 2, provided that the function g of x is equal to this quadratic relation x squared minus 5x plus 1. So the first thing that we can do is find the derivative of g at any point x, and then substitute the value of 2 into that answer once we get it, and that's going to give us the slope of the tangent line. And even if you have just the slope, you can actually find the actual equation of that tangent line if you have the actual functional value at that domain point, which we will eventually do today. So the derivative of the function g at any point x, we already know is going to be the limit as epsilon approaches 0 of g of x plus h, so that's going to be equal to what? So we're going to be replacing x with x plus h everywhere we see x in that relation. So that's going to be equal to x plus h, the quantity squared, minus 5, and that should be x plus epsilon, since we're using epsilon. So x plus epsilon, and then plus 1, and then minus g of x, that's going to be equal to x squared minus 5x plus 1 all over epsilon. So once we expand that, that's going to give us what? So that's going to give us x squared plus 2x epsilon plus epsilon squared, so that's the first term, and then distribute that negative sign, so minus 5x minus 5 epsilon plus 1, and then we're going to distribute that negative sign, so minus x squared plus 5x minus 1 all over epsilon. So if you notice here, we have an x squared that's going to cancel, which is very nice. We have a 5x that's going to cancel, and we're going to have a 1 that's going to cancel. And you should be left with only things that have your epsilon term in them. So we're going to have the limit as epsilon approaches 0 of 2x epsilon plus epsilon squared minus 5 epsilon all over epsilon. And we obviously can factor out an epsilon out of the numerator, so we're going to have epsilon times 2x plus epsilon minus 5 over epsilon. And we can cancel out those epsilons, and then we can take our limit. So we're going to be left with the limit as epsilon approaches 0 of 2x plus epsilon minus 5. So this epsilon is going to go to 0, and then we're just going to be left with 2x minus 5, which is the derivative of x squared minus 5x plus 1. So once we have the derivative, we can evaluate that derivative at any point we want. Therefore, the derivative of g at x is equal to 2 is just going to be equal to 2 times 2 minus 5, which is just going to be 4 minus 5, which is negative 1, which is going to be the slope of our tangent line. So what exactly is the equation of this tangent line, right? So we already know that x is equal to 2, so what's the y value at that point? So we're going to find the y value at that point by plugging 2 into the original function g. So that's going to be equal to 2 squared minus 5 times 2 plus 1, which is going to be 4 minus 10 plus 1, which is negative 6 plus 1, which is going to be equal to minus 5. So our point of interest is 2 minus 5. The slope of our tangent line is going to be equal to minus 1. Therefore, via these two pieces of information, we should be able to find the equation of that tangent line. So the equation of the tangent line, which I'm going to be calling LT, is going to have the form y is equal to mx plus some vertical intercept b, which we don't know. But we can use this point to our advantage because y is equal to minus 5, x is equal to 2, and we can solve this equation for b. So we have negative 2 on the right-hand side, so we can add 2 to both sides of that equation. So we're going to have minus 3 is equal to the vertical intercept. Therefore, the equation of the line tangent to the curve at the point 2 minus 5 is going to be given by the equation y is equal to minus x minus 3. Right? So that's our equation of our tangent line. And of course, we can obviously accompany this with a nice little graph. Right, so our parabola is going to be something like this. X is equal to 2 is going to be somewhere over here. And notice that the slope should be equal to negative 1. So if we look at that point, and we already know that it has a y value of minus 5, the slope of the tangent line should be negative, and indeed it is. And we've already found that the slope of this line is negative 1, and this particular line has an equation y is equal to minus x minus 3 for this particular relation g of x, which was given to be x squared minus 5x plus 1. Since finding derivatives are going to be very, very important throughout this course, having shortcuts or very fast ways of calculating derivatives of differentiable functions is actually going to be very, very important for time purposes. So obviously, the derivative of a function gives you the slope of the function at a particular point. But what if you have two functions that are added or subtracted to one another, and somebody asks you to find the derivative of the sum or differences of those functions? Is there a fast way to find the derivative of the sum or difference of functions if you know the derivative of the individual functions f and g at a particular point? And the answer is yes. Intuition says that hopefully we can distribute derivatives over sums and differences just like we do just multiplication over addition and subtraction, and derivatives actually do have that property. So let's give a brief proof or derivation of that rule just to convince ourselves that it actually does work. So what is the derivative of the sum or difference of two functions? I'm going to just be focusing on the sum rule here, but you could actually do a similar proof for the difference in case you're interested in. So this would be equal to the limit as epsilon goes to 0 of the function of interest, which is going to be the sum, evaluated at x plus epsilon. So we're going to have f of x plus epsilon plus g of x plus epsilon, and then minus the function of interest, which is f of x plus g of x all over epsilon. So what I'm going to do is I'm going to distribute that negative sign. So we're going to have the limit as epsilon approaches 0 of f of x plus epsilon plus g of x plus epsilon minus f of x minus g of x all divided by epsilon. Now what I'm going to do is I'm going to associate the f's together and I'm going to associate the g's together, and then I'm going to distribute this fraction into two smaller fractions. So I'm going to write this as the limit as epsilon approaches 0 of f of x plus epsilon minus f of x all divided by epsilon, and I'm also going to distribute the limit over the sum and difference as well, and then we're going to have plus the limit as epsilon approaches 0 of g of x plus epsilon minus g of x all divided by epsilon. But you should notice that that's precisely the definition of the derivative of f at the point x plus the derivative of the function g at the point x. Therefore, derivatives do distribute over addition, which is very, very nice. And you could, of course, prove it similarly for the difference, and this gives us what we refer to as the sum and difference rules for derivatives. And this says that the derivative of the function f plus g, so let's just write it like that, f of x plus or minus g of x, is going to be equal to the derivative of f at x plus the derivative of g at x. And keep in mind the derivative has to be the same exact point. Now let's introduce another rule that is quite useful, especially for polynomials, but we need to recall a special relationship from foundational mathematics. Recall that if we have the expression x plus epsilon raised to the power of n, where n is a natural number, then by the binomial expansion theorem, this is just going to be equal to the sum from k is equal to 0 to n of the n-kth binomial coefficient times x to the power of k times epsilon to the power of n minus k. Right? So in terms of a quick demonstration of how to use this, so for example, a plus b to the power of 3 is going to be equal to a cubed plus 3a squared b plus 3ab squared plus b cubed at the very end. And you can find each of these coefficients, 1, 3, 3, and 1, by using the general relationship that c and k is equal to n factorial, k factorial, n minus k factorial, with the emphasis that this only applies to natural numbers. So what we're going to do is we're going to use this nice little trick to prove another important rule in single variable differentiation. So what is the derivative of a monomial expression where n is a natural number? And later we can actually extend this to any real number also. So this is going to be equal to the limit as epsilon approaches 0 of x plus epsilon to the power of m minus x to the n all divided by epsilon. And again, n is a natural number. So what we can do is we can expand that via the binomial theorem. So this is going to be equal to the limit as epsilon approaches 0 of x to the power of n plus cn1 times xm minus 1 epsilon plus cn2 times xm minus 2 epsilon squared. And this is going to continue all the way down to cnn times x to the power of n minus m, which is just going to be equal to 0. So we're not going to write that. We're just going to write the epsilon term. So we're just going to have epsilon to the power of n. So that's the expansion of x plus epsilon to the power of n. And then we're going to have x to the power of n all divided by epsilon. Obviously, we have these x to the n terms, which are going to cancel, which is nice. And notice that every single term here is going to have an epsilon in it, so those are going to cancel. And then we're going to be left with the limits as epsilon approaches 0 of cn1 times x to the n minus 1 plus, and then notice every term in the second half, excluding the first term, is still going to have an epsilon in it. So I'm just going to factor that epsilon out. I'm just going to be left with cn2 x to the n minus 2. And then we're going to have, for example, cn3 xm minus 3 epsilon. And that's going to continue all the way down to cnn epsilon to the n minus 1. So notice, when we take the limit as epsilon approaches 0, this is going to go to 0 and delete all of that, regardless of what those cn's are equal to. And then we're just going to be left with cn1 xm minus 1. But what is cn1? Well, that's just going to be equal to n factorial, 1 factorial, m minus 1, the quantity factorial, which is just n times m minus 1 times m minus 2 down to 1. All over m minus 1 times m minus 2 all the way down to 1. Obviously everything cancels except for the lonely little n on top. Therefore this is just a fancy way of saying nx to the n minus 1. And therefore this gives us what we refer to as the power rule for derivatives, which says that the derivative of x to the power of n at a point x is just going to be equal to n times x to the m minus 1. Let's assume that somebody asks you, what is the derivative of a constant? Derivative of 5, derivative of pi, derivative of e, derivative of 1/2. Something that doesn't have any x's in it. What would you say? So if you think of this from the graphical interpretation, all constants have a graph that is associated to a horizontal line, and we know that the slope of horizontal lines is always equal to 0, regardless of what that constant is equal to. But we can of course prove this from the limit definition, because this is just going to be equal to the limit as epsilon approaches 0 of f of x plus h, or f of x plus epsilon, which doesn't have any x's in it, so that's just going to be equal to c, minus the entire function c, all divided by epsilon. But that's obviously just going to be equal to 0 divided by epsilon, as the limit as epsilon goes to 0. But that's just going to be equal to 0 before we even take the limit, so that still is equal to 0, right? With a special point at 0 if you consider the 0 divided by 0 case, which some people try to avoid anyway. So, at least from the graphical interpretation, we can easily see the derivative of constants are equal to 0. Let's combine this observation with the power rule and see if we can take the derivative of an arbitrary polynomial. Let's assume that somebody asks you, what is the derivative of the polynomial x to the 5th minus 3x to the power of 4 minus 2x to the power of 3 plus 2x to the power of 2 plus 5x plus the constant 8 evaluated at an arbitrary point x in the domain of this polynomial. So we already know that we can distribute derivatives over sums and differences and take the derivative of each of these functions term by term. Now, I just want to say ahead of time, you cannot always do this, and also rarely do this, with multiplication and division, only subtraction and multiplication. So by the power rule, we know that the derivative of x to the 5th is going to be 5x to the power of 4. The derivative of minus 3x to the power of 4 is going to be equal to minus 3 times 4, which is minus 12x to the power of 3. 2 times 3 is going to be equal to minus 6 to the power of 2. 2 times 2, which is going to be 4 times x to the power of 1. And then the derivative of 5x is going to be equal to 5 because the slope of 5x is always equal to 5, regardless of the points that you choose. And the derivative of 8 is equal to 0, so that disappears. Therefore, that's going to be the derivative of your particular relation. Now, let us look at another example just to make sure we're comfortable with finding the derivative of these polynomials. So let us assume we're interested in finding the equation of the tangent line and also normal line. Normal line actually has quite a few physics applications and some other fields too. Tangent lines obviously grates the curve at exactly one point near that point in its domain. Normal lines are going to be perpendicular to tangent lines, so the only difference is just going to be the slope of these two. And let's assume we want to find the tangent line and normal line to the function f of x is equal to x cubed minus 5x squared plus 7x minus 4 at the point 2 f of 2, and we obviously can find what f of 2 is quite easily. So what is f of 2? So f of 2 is going to be equal to 2 cubed minus 5 times 2 squared plus 7 times 2 minus 4. So that's going to give us 8 minus 4 times 5 is going to be 20. And then we have the 14 minus the 4. So we have a positive 10, that's going to give us a negative 10, and then plus 8, that's going to give us negative 2. So the point of interest that we're going to be finding the tangent and normal line at is going to be the point 2 minus 2. So let's just keep that point in the back of our minds for now. The next thing that we need to find is the derivative of this function at the point when x is equal to 2. So the derivative of this function, x cubed minus 5x squared plus 7x minus 4, is going to be equal to 3x squared minus 10x plus 7. That means the derivative when x is equal to 2 of this function f of x is going to be equal to 3 times 2 squared minus 10 times 2 plus 7. So that's going to be equal to 3 times 4, which is 12, minus 20 plus 7, which is negative 8 plus 7, which is going to be equal to minus 1. So this is the slope of the line tangent to the curve at the point 2 minus 2. So let's get into this. So the slope of our tangent line is going to be equal to minus 1, and the slope of our normal line is going to be the negative reciprocal of that slope, so that's going to be equal to positive 1. So that's going to be our slopes for our tangent and normal lines, so we just need to find the associated y-intercepts for each of those lines. Let's start with the point for the tangent line. And again, keep in mind the point of interest is going to be 2 minus 2. So the slope of the tangent line, or the line is going to have the equation y is equal to minus x plus some number b, and we can use that point as usual. So we're going to have minus 2 is equal to minus times 2 plus b, and obviously if we add 2 to both sides of this equation, we get b is equal to 0. And for a normal line, our equation is going to be y is equal to positive 1x plus b, and if we use that point again, minus 2 is equal to 1 times 2 plus b, and subtract 2 from both sides, we're going to have that b is equal to minus 4. So therefore, the equation of the line tangent to the curve is going to be equal to y is equal to minus x plus 0, or we could just say minus x, and the equation of our normal line is going to be equal to y is equal to positive 1 times x minus 4. So that's our equation of our tangent and our normal lines. Let's just do a quick accompanying graph just to make sure we understand exactly what we're looking at here. Let's draw our curve, which is going to have this type of graph. And our point of interest is going to be located somewhere around here. So that's going to be 2 minus 2. Our tangent line is going to be looking something like that. So this is going to be equal to, and technically it should be passing through the origin, right? So let's just fix that. So this is the line y is equal to minus x. And then the tangent line, or the normal line, is going to be perpendicular to that blue line. So that has to make a right angle. And this line is the line y is equal to x minus 4. So if we are to extend this horizontal or vertical axis, then that value there is going to be minus 4. So that's how you can find the tangent and normal lines to a curve using derivatives, and obviously these rules only apply to constant and polynomial functions. And for all other functions, we'll of course eventually look at rules for each of them. The last thing I want to mention in this brief introduction to derivatives are just a couple different notational things that some different people will use to notate the derivative of a function f at a given point. Obviously, this notation makes a lot of sense. It gives us the slope of the function f when x is equal to a particular number. But obviously, if we have an arbitrary relation like this, and I say find the slope of the tangent line when x is equal to 2, obviously you're going to have more than one answer. Because obviously in this picture, we're going to have that slope there, and we have that slope there, which obviously can be very, very different from each other. So this notation should only be used for functions. Okay? Another thing that I also want to mention is just to give you a little bit of insight into what we're actually looking at here. So if we look at this in the form before we simplified the denominator, this was just equal to the limit as epsilon approaches 0 of f of x plus epsilon minus f of x divided by x plus epsilon minus x. Notice that the numerator of this function is just a subtle change in the function f divided by a subtle change in the value of x. So we can actually look at this from the incremental perspective and say that that is just a change in f divided by a change in x. Obviously, delta f and delta x would just be finite changes, but we actually want to look at infinitesimal changes, i.e. when epsilon goes to 0. Therefore, some people will use a different notation and say that, okay, as delta x goes to 0, we will just denote that as dx, and as delta f of x goes to 0, or as delta x goes to 0, we're just going to denote delta f of x as just df of x. So this is just notating an infinitesimal change in x results in an infinitesimal change in f, right? And some people will look at the f as a different thing and just write this as d over dx of f of x. And that is also a notation that some people use, and you may even see some people notate this as f prime of x, which I do not recommend because once you get to multiple variables, when you say prime, is that the derivative with respect to x, y, z, t, or in some arbitrary direction? We don't know. So let's actually look at a couple examples just to summarize these different notations. So for example, let us assume that f of x is equal to 3x squared minus 5x plus 1. So if somebody asks you what is f prime of x, since there's only one variable here in terms of x, this is usually going to be notated as equivalent interpretation of the derivative of f at a particular point. So these would be equivalent provided that there's only one variable, in particular x, being mentioned here. So that's obviously just going to be equal to 6x minus 5. Let's assume that somebody else asks you, okay, if, let's say, I don't know, let's say we have y is equal to 5x to the 7th plus 5x cubed minus 2x plus pi. And someone asks you, what is dy divided by dx? And you're like, well, what exactly is this? Well, this expression obviously is a relation, and it indeed is a function. Therefore, we can call this relation f and label that as just f of x, right? Since it is a function, since we have y is equal to something with only x in it. Therefore, in this particular case, this can be viewed as equivalent of the derivative with respect to x of y, which is technically the derivative with respect to x of 5x to the 7 plus 5x cubed minus 2x plus pi, which is obviously just going to be equal to 7 times 5, which is going to be equal to 35x to the 6th plus 15x squared minus 2 plus 0, and that would give you that particular answer as well. So if you see any of these notations, in particular the derivative of f with respect to x, the derivative of f of x with respect to x, the derivative with respect to x of f of x, or you see that dy divided by dx where y is a function of x, all of these things are mentioning the same exact thing most likely, provided that they all have useful meaning in their associated context, but some have pros and cons over others. So that's just a brief introduction to the derivatives of single variable functions. There's definitely so many other properties that we're going to be working through, but these are just some of the fundamentals that you definitely should know. So I'll see you in the next video. Take care.